We started our study of numbers with some really basic sets. They include numbers we have been using since childhood, either to count our toys or to count how many days were left until our birthday, so we could get more toys. But as grown-ups, we also use them to solve equations. For example, solving for x gives us a number that may belong to the natural set, or perhaps it's a whole number, depending on the equation. And for some equations, the solution may even be negative. Well, that has worked for us so far. Let's see if the case remains. First, let's simplify this equation. And we get x as 3 upon 2. But hey, that's a fraction. And although we literally have countless numbers in our sets, they still don't have fractions. What to do? Enter rational numbers. Rational numbers are the set of both fractions and integers, represented by the letter Q. And there is a special way to express it. First, write a fraction a upon b, such that a and b are the elements of set z. The vertical line is a symbol used for such that, whereas the straight symbol, which kind of resembles a backwards E, stands for our elements of. Now, also remember that the denominator can't be 0. Otherwise, the fraction will be undefined. And you're done. A smart way to express set Q. Now, with this, you can solve any equation where the value of x is some number divided by another number. Not just that, they even represent whole numbers and decimals, as long as they can take the form a upon b. However, is this set the final one? Well, no. There are numbers that are not rational. That is, they can't be written as fractions. So, we call them the irrational numbers, represented by Q dash. You must be wondering what kind of numbers are these? At first, they are the square roots of all prime numbers or imperfect squares, like the value of x for this equation. If it would have been the perfect squares, like 4 or 25, only then it can take the form a upon b. Secondly, non-terminating decimals are irrational. Like if you consider computing the same radical, you will find that it never ends, which again means that converting it into a fraction is impossible. On the contrary, if there would have been terminating decimals, they can be written as fractions, like this little decimal here, or even this really big one. Some might ask, hey, what about 1 upon 3? It also doesn't terminate, but is a fraction too. Well, this brings a slight modification to the second point. Irrational decimals are not just non-terminating, but at the same time, they are non-recurring too. But what does that mean? See 1 upon 3 again. It is not irrational, although it is non-terminating, because 3 repeats or recur. A decimal like this one is called recurring, and it can always be written as a fraction. Hence comes under the category of rational numbers. But numbers like root 2 again, that neither terminate nor recur, are irrational numbers. Can you tell if this number is irrational? Yes, without a doubt. How about this one? You don't even need to convert it to tell because root 5 is irrational according to the first point. The square roots of all prime numbers are irrational. For the same reason, this one is irrational too. Now that we have learned what rational and irrational numbers are, we are going to combine them into one giant set. We call this the set of real numbers, denoted by a fancy looking R. It contains all the numbers we have seen so far: irrational, rational, integers, whole, and natural. It sounds strange to call numbers real, as though some numbers only exist in our imagination. The funny thing is, there is such a thing as imaginary numbers. But don't worry, they are for our next lesson. We will stay in reality for now.